Our sun is just one star among countless others in the Milky Way galaxy. And around many of those stars, there could be planets much like Earth or perhaps even more hospitable to life. But all of them are so incredibly far away that they appear as mere points of light in our sky. But astronomers have managed to discover thousands of these distant exoplanets. So what makes them think that they can actually detect planets that far away? How do they study them at all? And have they found anything interesting yet? You'll find out in this video. How to detect an extraterrestrial world. First, we need to get an idea of the scale of the problem. The Sun is around 150 million kilometers from Earth, but the nearest star to us, Proxima Centauri, is located more than 4 light-years away. And if we were to replace the Sun with any random star in the night sky, we would still be able to see it only as a point of light. Because even though some stars are thousands of times larger than our Sun, they are also thousands of times more distant from us. So all the light from these stars reaches us as a single ray, and that is why we can see them as points of light rather than as disks. The only exception is the planets in our solar system. They are relatively close to us, and their angular diameter is large enough for us to resolve them as disks. But even that is not easy to do. We can easily distinguish Mercury, Venus, and Mars from each other only with the help of a telescope. However, no telescope currently in operation on Earth can resolve a planet orbiting another star into a disk. For that, we would need a telescope over 300,000 kilometers in diameter. For comparison, the largest optical wavelength telescope currently in operation on Earth is just 39 meters in diameter. It is the extremely large telescope at the European Southern Observatory in Chile. Meanwhile, the size of the Moon is just 3,474 kilometers, and the Earth's equator is just 40,075 kilometers. So how did astronomers manage to take pictures of exoplanets if they cannot be resolved into disks? Let's take a look. Direct observation. The first direct images of exoplanets were taken in 2004. They were the planets 2M1207b and Fomalhaut b. By the way, the image of Fomalhaut b was taken by the same telescope that spotted the asteroid belt of our solar system. That's the reason why the asteroid belt lies beyond Neptune. And in 2017, the European Southern Observatory released this collage depicting 17 exoplanets. All these images were taken with the same instrument, the Very Large Telescope. In all of these cases, the key to taking pictures of exoplanets was that the parent stars were either faint or relatively close to Earth. But these methods are not suitable for most stars in the night sky, including the Sun. We can take pictures of exoplanets orbiting nearby red dwarfs, but there aren't many of those stars. And besides, red dwarfs are small, dim stars. There is hardly ever any talk of planets orbiting stars, like the Sun being imaged directly. So how exactly did they manage to spot them? Indirect observation methods. The first method used to detect exoplanets indirectly is the transit method. It was used to discover the first exoplanet orbiting a solar-type star back in 1995. But what is the transit method? The transit method is based on observing the dimming of a star's light. When a planet passes between the Earth and the star, if the size of the planet is much smaller than the size of the star, from our perspective, then the star will appear to flicker briefly, as if someone is winking at us. In reality, the light of the star passes through the planet's atmosphere and is slightly scattered by it. That is why the star seems to wink at us. Moreover, when a planet passes between the Sun and Earth, its gravity affects the star's light waves, which results in a slight change in the star's spectrum. This phenomenon is called gravitational lensing. Both the dimming of starlight and changes in the spectrum allow astronomers to calculate the size of the planet and its distance from Earth. Unfortunately, the transit method only confirms the presence of an exoplanet. To determine the planet's mass, astronomers use the radial velocity method. The radial velocity method. As I said before, all stars in the night sky seem to be points of light. However, if we analyze the spectrum of starlight, we can see that every star exhibits a slight Doppler shift. This means that light waves coming from stars are slightly shifted towards the blue or red part of the spectrum. And since this shift depends on the speed of the star's movement, such a shift tells us whether the star is moving towards us or away from us. Now let's imagine that the star is orbited by a planet. Because of its gravity, the star will be constantly pulled towards the planet and move faster precisely when it is closer to the planet. At the same time, the planet will also pull the star away from it, and the star will move slower. Thus, the star's movement will be periodically distorted, and this distortion will affect the spectrum of starlight. This change in the spectrum can be easily detected with modern instruments. Using this method, astronomers calculated the mass of the first exoplanet, 51 Pegasi b, which is more than twice the mass of Jupiter. Currently, this method is the main tool for finding exoplanets. And here is why. According to astrophysicists, there can be several planets in orbit around one star. Each of them will cause a shift in the spectrum of starlight. But the effect will be weaker the more massive the planet is, and the farther away from the star it orbits. To identify such planets, we need very sensitive instruments. And although the transit method allows us to see planets of any mass, they must be in a favorable position relative to the Sun and Earth, otherwise we won't be able to notice the change in the star's brightness. This is why we use both methods together. First, we find the planet using the radial velocity method, and then we determine its size using the transit method. And that is exactly how they managed to find thousands of exoplanets. What have they found? Recently, astronomers have discovered something incredible.
They found an exoplanet that is almost exactly like Earth. Let's take a look.
Wolf-Rayet. Wolf-Rayet is a binary star system located 8,000 light-years from Earth. It consists of two stars of different sizes. One of them is an O-type star, and the other is a B-type star. Exactly 11 days ago, a transit of an exoplanet in front of these stars was recorded. But this is not the most interesting part. The thing is that, during the time of observation, the binary star system had already passed its peak brightness. This suggests that the brightness of the entire system decreases periodically. That is, an object much larger than the planet could be orbiting these stars. However, the period of revolution of this object is 260 days. Such a short period indicates that this object is located very close to the stars. According to astrophysicists, the minimum distance from this body to the nearest star is at least 10 astronomical units. For comparison, the distance from the Sun to Neptune is 30 astronomical units. That is why the object in question cannot be a planet. Most likely it is a brown dwarf. But if it's a brown dwarf, then where's the planet? In fact, the researchers believe that the planet is in the habitable zone of Wolf-Rayet. The planet's hypothetical orbit could pass between the hottest and coldest regions. There are three potential candidates for this role: WR1206b, WR1206c, and WR1206d. The width of the habitable zone of Wolf-Rayet is much smaller than that of our solar system, which means that the planet is unlikely to be much further away from the stars. Fortunately, the James Webb Space Telescope is scheduled to launch soon, and it will be able to measure the spectrum of the Wolf-Rayet system. With its help, we will know for sure whether there is a planet in the habitable zone of Wolf-Rayet, in addition to finding potentially habitable planets. Scientists also found planets that could have liquid water under their ice. Such a planet is WASP-33b. Observations show that the planet receives heat from its star, which heats the side facing the star to 160 degrees Celsius, while the other side is shrouded in perpetual darkness and ice. At the boundary between the two hemispheres, there could be a strip of land where the temperature is quite comfortable, and there could be liquid water there. Sounds pretty cool. Does anyone want to join me on an expedition to WASP-33b? Leave your answer in the comments below. Don't forget to subscribe for more videos about space.